They're somewhere like 1 trillion to 1 quadrillion times as strong as the magnetic field of the Earth.
In this video, I got the chance to talk to Dr. Andrew Cameron about pulsars and neutron stars. Dr. Andrew Cameron completed his PhD at the Max Planck Institute and is now working at the Swinburne University of Technology studying pulsars and general relativity. Now you might be thinking, how do pulsars form? Well, that's what Dr. Cameron will answer in today's video. Thank you so much for joining us, Andrew. What are the different types of pulsars, and how do we know which type a particular pulsar is?
Well, there's lots of different ways to characterize types of pulsars, but there's one pretty easy place to start, and I'll skip back a few slides for this. Spoiler alert, you've pretty just seen stuff there. So every pulsar has a rotational period. It's spinning at some particular spin period from, tens of seconds down to the order of milliseconds. But they're not just spinning at a constant rate. They are, in fact, all slowing down at some particular rate as well, because they are losing energy to their radio emission. That energy has to come from somewhere, and it's being drawn from the pulsar's rotational energy. So by characterizing a pulsar by its spin rate and its spin down, also called the spin derivative or the p dot, we can get a diagram like the one on the left here called a p dot diagram, where you've got the spin rate on the horizontal axis and the spin derivative on the vertical axis. And you can see a few patterns emerging from the pulsars on this diagram already. And we can use this to characterize certain types of pulsars. The first one is the big cluster in the middle of the diagram. These are called the quote-unquote normal pulsars, or the canonical pulsars. Now, these pulsars are typically found by themselves. They're isolated. They don't have any kind of binary companion. As I mentioned before, they're born towards the top left of the distribution at around short spin periods of 30 milliseconds or so. And then over the course of a few 100 million years, they will gradually slow down, moving towards the bottom right, until eventually they spin down to slow enough rates of rotation that they can't sustain their radio emission anymore, and they turn off. They enter what's called the pulsar graveyard, although that concept in itself is still being ironed out. It's not perfectly understood how and why pulsars turn off. Another family of pulsars down towards the bottom left, all here, a lot of them identified with their little red outlines. These are the millisecond pulsars. The red circles around each dot there show off the ones that have a binary association. And you can see that most of the binary pulsars on this chart are found in the millisecond pulsar region. And the reason for that is that these millisecond pulsars, which have been spun up to very fast rates of rotation, need a binary companion to get to that rate of rotation. So what will happen is you have a pulsar that is from the normal family of pulsars up in the first type of pulsar, and it's got some main sequence binary companion, like our own sun, for example. And as that binary companion gets older, it will eventually start to swell up as it gets older, and eventually the material from the outside of that companion star may become gravitationally attracted to the companion pulsar. The star will have expanded so far that the pulsar's gravity becomes stronger. And we call that overflowing the companion's Roche lobe. The Roche lobe is the region of the star's gravitational influence. So what happens is that companion star starts donating material which gets accreted onto the pulsar, and that accretion process, again by the process of conservation of angular momentum, spins that pulsar up to really rapid rates of rotation until eventually that companion star dies at the end of its life. Most commonly, it becomes a white dwarf, although a few of them do eventually have their own supernova event as well. And the millisecond pulsars are mostly produced from those white dwarf producing companion stars. They spin really fast, as I mentioned already. The fastest one we know about is about 716 hertz, which is about 1.4 milliseconds for one rotation of the pulsar. So it's rotating about 716 times a second. To put that in perspective, that would mean that at the surface of the neutron star, it's rotating at about 15% the speed of light at the equator. These are ridiculously fast rates of rotation. And they're also extremely stable. The rates of spin down are significantly decreased as compared to the normal family of pulsars, such that they will keep spinning longer than the current age of the universe before eventually they turn off. And one nice advantage of that is it makes them really useful clocks, because they are really stable in their rotation. In fact, some of the precision of their rotation rivals that of our best atomic clocks here on the Earth. And so they can be really useful for doing astrophysical applications which involve keeping good time precision. And we can come to that later on in the presentation. One other type of pulsars are the magnetars. Now, not every magnetar is a pulsar, but some of them are. They don't all emit in the radio, and normally pulsars are considered to have radio emission. So They're up at the top right of the diagram. They're indicated with these green triangles. And what makes magnetars distinct is they have exceptionally high magnetic fields. So your average pulsar might have a magnetic field that is, say, 10 million times stronger than that of the Earth. Magnetars take that up another level. They're somewhere like 1 trillion to 1 quadrillion times as strong as the magnetic field of the Earth. They are the most magnetic things in the known universe. And they're also extremely energetic. They're often associated with energy emissions in gamma rays and X-rays. They're not so common in radio, although we do know of some that do emit radio as well. And another difference is that they're not powered the same way pulsars, conventional pulsars are. They're not powered by that drawing of energy from the pulsar's rotation. Instead, they're powered directly by the decay of the magnetar's magnetic field. Now, one of the nice things about magnetars is that we think they might be one of the origins of a thing called fast radio bursts, which I believe you've discussed on an earlier episode with Chris Flynn. They're these millisecond bursts of radio energy that come from distant galaxies out in the universe. They look a lot like pulsars in their individual structure, but they often occur only once or sporadically from objects in distant galaxies that we don't properly understand yet. One interesting thing about magnetars, though, is that we saw a very FRB-like radio flare from one of these magnetars in our own galaxy only a couple of years ago, back in 2020. You can see the reference listed down there for the 2 publications which documented that discovery. And so it lent a lot of weight to an earlier hypothesis that magnetars might be one of the causes of the FRBs that we see in other galaxies. Zooming back out a little bit as the last type that I want to discuss here, there are more broadly just binary pulsars as a whole. Now, you've seen that a lot of them are associated with the millisecond pulsars down at the bottom left of the diagram, but they can occur in other types of pulsars as well. You can see a few of them scattered through the normal pulsars as well. So you can have a binary pulsar is essentially just a pulsar that is orbiting something else. And most commonly, that's a white dwarf, hence the association with all the ones down in the bottom left. But there are other kinds of things that pulsars can have orbiting them as well. One interesting one is that pulsars can have exoplanets going around them. And in actual fact, although we know something like several thousands of exoplanets that have been found so far, usually by optical telescopes, the first exoplanets were found by a pulsar or by observations of a pulsar back in the early 90s. We were able to measure the very slight wobble that those exoplanets were causing to that pulsar thanks to their gravitational influence, and the way in which that wobble was offsetting the pulse times of arrival as they came to the Earth. And so we were able to conclusively show that a pulsar had planets going around it before anybody else had found any exoplanets. So pulsars have a unique claim to fame there. There are other pulsars that are orbiting things like main sequence stars, although those are fairly rare, though I'm studying a few of them in my own research right now. And there are a few dozen examples of where a pulsar is orbiting another neutron star. Those neutron stars may or may not be pulsars themselves. We've only got one example where one of those pulsars is orbiting another pulsar, although the second pulsar in that binary system has since tilted out of view, so we can't see the pulsations anymore. The other neutron star binaries we have, the companion neutron star might be a pulsar, but it might not just be pointing at us. Or it may have been a pulsar in the past, but it's since turned off. We don't know. The last item in that list I've got with a question mark there is the Pulsar-Black Hole binary, and that's got a question mark because so far we haven't found one. We think they should exist, although only in very small numbers. They might be on the order of, say, 1 to 10 in our galaxy alone, and so far we haven't found any. Finding one, though, would be really, really, really cool. Because one, it would verify that our models of pulsar formation that predict this can happen are correct. And secondly, if we found one in the right conditions, it would allow us to do some really amazing scientific applications like testing theories of gravity in extreme environments that you just can't get anywhere else. We know from measurements from LIGO, the gravitational wave detectors, that in other galaxies, we have seen what we think are neutron stars and black holes that are orbiting each other and merging together. So we know it can happen. But as far as finding it in the radio domain in our own galaxy, hasn't happened yet. And it's a little bit of one of these, what are considered the holy grails of pulsar astronomy, is that we'd love to find one of these things, but no one's found one in the 55 years of pulsar study so far.
I guess one of our viewers might just happen to find it in the next 10 years.
So if you do it, I'll buy you a drink. It's everyone's dream. Well, not everyone's, but it is certainly a particularly high achievement in the field if you manage to pull it off.
Nobel Prize? Is that how high it is?
Well, that's hard to predict, and I wouldn't give any guarantees there, but certainly a very well-received publication in something like Nature, I think.
Wow. That is really fascinating, and it just provides a little bit of that motivation for people who are really interested in astronomy but don't really know which field they want to go in.
If you haven't checked out the previous podcast episode, then make sure to do that by clicking here. Make sure to subscribe, like, share, and comment down below. Trust me, I'll respond. Test me.